In our next session, we will take a look at Cisco's next generation encryption, NGE. And our session is going to start with an overview of so-called Suite B set of cryptographic standards, which is, as we will see, gonna make kind of like a baseline for next generation encryption. So we will also discuss NGE, and then we will also take a look at some specific recommendations as how Suite B and also next generation encryption functions should be used to protect our data. And this stuff is going to be applicable to IPsec and TLS. Okay, so let's go ahead and talk about Suite B first, because Suite B, as we will see, is going to be used by next generation encryption, at least partially. So Suite B is essentially a set of cryptographic standards that were selected by US government, by National Security Agency, for secure communication over untrusted networks like, for example, the internet. And this set of algorithms secure cryptographic functions, which is going to be, as we will see, mostly based on AES for encryption and SHA-2 for integrity. Those functions are generally supposed to meet future needs. So they are supposed to be valid for a certain amount of time, and they are supposed to be secure during this time. And this is something that NSA thinks is sufficient to protect confidential information at the secret and top secret level. Okay, so in terms of the actual components, or just the algorithms that fall under Suite B standard, for encryption, as I said, it is going to be primarily AES, and specifically it's going to be 128 and 256-bit key variation of AES. And we are going to be talking about Gallo counter mode or Gallo message authentication code, so not CBC. Then for hashing, we're going to focus on SHA-2. We are no longer using MD5 or SHA-1. And then for digital signatures, recommendation is going to be to use the elliptic curve with DSA, 256 or 384-bit keys. And for key exchange, we will use Diffie-Hellman, but also the elliptic curve variation of this function. Okay, now what Cisco did at some point, it was back in 2011, they came up with a somewhat similar concept to Suite B, which is known as next generation encryption. So next generation encryption is what Cisco thinks is gonna be secure. This is also a set of cryptographic standards that are deemed to be secure in case of NGE, specifically for the next 2 decades. So again, it was created back in 2011. So it is supposed to be valid. I mean, the functions that are part of this standard, they should be valid until around 2030. And those functions are based on the Suite B standard. Cisco's logic is that, well, to kind of like help their customers to become compliant with Suite B specification, which is commonly implemented by many of the regular compliance standards, such as HIPAA, maybe FIPS, PCI. Most of the functions that they put into NGE, this is going to be stuff taken directly from Suite B, so that when their customers will actually follow NGE, they will kind of like automatically become compliant with those different standards. So this is going to be especially important for certain government organizations that have to be compliant with Suite B specification. Okay, now in case of NGE, in addition to listing those individual functions that Cisco recommends to use for encryption, authentication, digital signatures, and so on, they also included the information about which of those individual algorithms are potentially deemed to be secure after the introduction of so-called quantum computers, QCs, which is, as of right now, a more of like a theoretical concept. But assuming that quantum computers would at some point become reality, certain functions from the NGE suite are still supposed to be valid, meaning not become compromised by those super fast computers, because this is what QC actually is. This is a super fast processing unit that is running much faster than regular computers. And now which of the algorithms Cisco thinks will be post-quantum secure or just quantum computer resistant? This is something that you can quickly check in their documentation. Actually, it's not part of the documentation. It's a separate portion of the Cisco's website, of the Cisco's portal, and they keep this information, they try to keep this information up to date. So the easiest way to find it is going to be to use Google. You will just say Cisco next generation encryption. And when you take a look at this document, they will actually show you a list of those different cryptographic functions. And they will tell you which of those are recommended, which of those algorithms are actually part of next generation encryption, and eventually what functions are theoretically supposed to be post-quantum resistant. Like for example, if we take a look at DES, they say this is for encryption, and the current status for this technology is avoid. Avoid means that you don't really want to use DES anymore. It is not secure function. Ideally, if you will switch to AES. Now for triple DES, they say this is obviously also for encryption. The status is legacy, which means that you can't possibly use it. Like if your software does not support AES, but as long as you have a chance to migrate, to switch to a newer alternative, you should immediately start using AES. And now in addition to that, if you are actually to use triple DES in your network, you should consider changing the key lifetime. You should make the lifetime of the key shorter, so perform the key on a more frequent basis, where shorter lifetime specifically says use a 30-minute interval for your keys. So change the keys every 30 minutes instead of, like for example, in case of IPsec, ID1, tunnel lifetime, it's 24 hours. It is too long for triple DES. Okay, for RC4, we see that it says don't use it. And now in case of AES, the status is acceptable for a cipher blockchaining, which means that it is okay to use it. This is a safe function. It is just not part of the next generation encryption. Versus AES in the GCM mode, it is part of NGE. This is what provides authenticated encryption, and this is what works very well in hardware. It operates very efficient at high data rates as opposed to CBC mode, and this is why actually GCM is part of next generation encryption where CBC is not. But both functions with 256-bit keys, they are supposed to be post-quantum resistant. Now for the asymmetric key cryptography, we see that the lower key lengths, they should no longer be used. Then for the moderate key lengths like 2048, it is okay to use them, but you ideally want to switch to elliptic curve variations of those. So for RSA and DSA, it is going to be EC-DSA, and then for Diffie-Hellman, it is going to be EC-Diffie-Hellman. And ideally, if you are actually to use, we take a look at the elliptic curve functions themselves. Ideally, if you're actually to use the 384 key, at least 384 bits for the key. So this is deemed as acceptable. Okay, what else? MD5, don't use it. SAJ, only use if you have to. Recommendation is going to be to use SAJ2 group of functions. This is what falls under next generation encryption for integrity. And note that 256 version is not deemed to be post-quantum secure, and because of that they recommend you to use SAJ 384. And then for hashed message authentication code variations of integrity, so this is when you will combine hashing with a key, they say don't use MD5. HMAC SAJ1 is okay to be used, but ideally you want to use the NGE version, which is HMAC-SAJ-256. And one more thing I want to discuss in this session, we will now also take a look at more specific recommendations as what actual suites should be used for encryption, integrity, and possibly key exchange for two commonly deployed technologies. This is going to be IPsec and secure browsing with SSL TLS. And we are going to start with IPsec. The actual details, you can find them inside of RFC 6379, which is Suite B, cryptographic suites for IPsec. And there are actually going to be two main suites that are recommended for usage for IPsec, where each of those suites is going to be listed in two different variations. So in case of Suite B GCM, we see that we are able to use it with a 128-bit key. This is going to be for AES, where the other variation is going to be to use a longer key of 256 bits, and the same is going to apply to the second suite. So now the way that we should read it is that we will actually take a look at the functions, the cryptographic algorithms for two different types of IPsec tunnels. For IPsec, which is going to be our data, and we will also take a look at it for phase 1 tunnel, the old style phase 1 tunnel, which is more of like a management connection for IPsec. So they say that for the data, what we should be using here in this first variation of Suite B GCM with a 128-bit key, for the data we should be using ESP encapsulation with AES encryption, where the key length is going to be set to 128 bits. We're going to be running this encryption in GCM mode, which is talking about authenticated encryption. So this means that integrity can be set to be null, because integrity is going to be inherently provided by our encryption. And now the second variation, at 256 of this suite, the only change here is that we will use encryption with a longer key. And now if we take a look at this for the management tunnel, the logic is going to be pretty similar. Whatever it is showing here in the parentheses, this is talking about the second version of this suite. So in case of encryption, we're going to be talking about a key consisting of 256 bits. It says use SAJ2 function with 384-bit output. And then for Diffie-Hellman, use a function with a 384-bit key in the elliptic curve modulo a prime, a version of Diffie-Hellman. And now elliptic curve modulo a prime, this is essentially one of the variations of elliptic curve functions, in this case for Diffie-Hellman, which is more efficient than the other one. So this is why they call it ECP. So again, whatever you see here in the parentheses, this is talking about the 256 variation versus everything we see without the parentheses, like over here or here, SAJ 256, the regular Diffie-Hellman. This is talking about 128 version of this suite. Note that for the management tunnel, it is talking about AES running in the cipher blockchaining mode, not GCM. Okay, and the very similar thing we will see here for the second suite. The main difference is that we are now talking about Gallo message authentication code, which is authentication / integrity, but not encryption. So this is talking about, as we will see in just a second, protection of the data packets. It says use AES either with 128 or 256-bit key running in the GMAC mode, which is going to provide authentication and integrity, and then encryption is going to be disabled. Like if you only want to authenticate, integrity, verify your data, but you don't want to encrypt them. And then for IKV2, and nothing is actually going to change here. The management tunnel is always supposed to be encrypted. So we will use AES in the CBC mode. We will perform integrity checks separately. And then Diffie-Hellman is used for key exchange. Okay, and a similar document that is recommending certain suites for TLS and DTLS. So this is going to be for secure browsing. It is going to be RFC 7525, recommendations for secure use of TLS, DTLS. First and foremost, what they say is that we should always try to avoid any of the SSL versions, like version 1, 2, 3. If they are all deemed as insecure, there are some known attacks that are successful against those versions. And now the reason why they say we should try to avoid TLS version 1.0 and 1.1, which corresponds to the TLS version 1.0, is that those newest functions like AES in the GCM mode are not supported by those protocols. So because of that, they say use TLS and DTLS versions 1.2, which is what will eventually allow you to run those Suite B / next generation encryption functions. Okay, and specifically in terms of the actual cipher suites, what they say you should be using is whatever provides forward secrecy and authenticated encryption. So authenticated encryption, again, this is talking about GCM mode, where forward secrecy, also known as perfect forward secrecy, and this is talking about ensuring that your current keys that you are using to protect your data are not based on the previous keys. Or in other words, it says that if the attacker is somehow able to compromise the current keys, it will not be able to easily guess or just compromise future keys, the keys that you will be using after renegotiation. So we know the keys, we will be changing them from time to time, especially like when you use some sort of key exchange protocol. And like, for example, in case of IPsec, if you don't use a forward secrecy, all keys are normally based on the keys derived in the previous exchange. So this is something that is deemed as a security vulnerability, and because of that, they no longer recommend to use functions that don't support PFS or just forward secrecy. So let's take a look at the actual ciphers. As you can see, it is going to be always Diffie-Hellman, either in the regular version or as one of the elliptic curve functions. It is always going to be RSA. For digital signatures, we are going to be using AES in the GCM mode in all variations here, and it is going to be done SAJ2 function 256 or 384. So SAJ and RSA, this is what is going to be used for the digital signatures for authentication and integrity. And then AES, GCM, this is our authenticated encryption. This is what you'll use for the data.